We have seen many times a 3x4 matrix determines a linear map from R4 to R3, right? In general, a m by n matrix determines a linear map from Rn to Rm. Here, m value is 3, n value is 4. Okay. So we'll work on question A first. So this time I'm not going to differentiate the meaning of the notations. By that I mean I'm going to use A to denote two things. One thing is the map, the 3x4 matrix. So the other thing is the linear map associated with A. Okay. In question A, I'm going to still use A to denote the linear map. Okay. Again, a 3x4 matrix determines a linear map from R4 to R3. Okay. We actually compute that from R4 to R3. The domain is R4. In R4, all vectors have 4 components. Again, I want to repeat, in R4, all vectors have 4 components. Okay. So any vector in R4. So now let's say any vector in R4. I'm going to use notations like so maybe x. Can use x1, x2, x3, x4. So I do not have to use x, y, z. I don't know the other one to choose. So maybe t. But I'm going to use t for other things. Again, for the people who joined the class late, on handout number 8, I included one more question. Okay. At this point, you do not have to download, so just try to follow me. The handout is always on D12. Okay. Again, A 3x4 matrix determines a linear map from R4 to R3. Okay, and every vector in R4 has 4 components: x1, x2, x3, and then x4. I'm going to use x1 through x4 to denote the 4 components of a arbitrary vector. And probably I'm going to make the brackets a little bit bigger. Now the rule is that every vector in R4 is mapped to the rule is given by the following, right? You multiply 2 matrices. So basically A on the left, A times x1, x2, right, x3, x4. That's the definition of the linear map associated with a given matrix. So because A is given, in most cases I'm looking for the rule in terms of the components. So by that I mean on scratch paper, okay, on scratch paper you compute A times x1, x2, x3, x4. I believe we have seen that too many times. You can do it mentally, okay. Again, the meaning of the rule is the following. A vector with 4 components in R4, x1, x2, x3, x4. A vector in R4 is mapped to, you are looking for a vector in R3. The vector in R3 is computed using A times the input. A times the input. So can I say it that way? Anybody want to tell me the first component? As long as you can see the first component, then you know what's going on. So please, anybody want to tell me after multiplying A and the input, what is the first component? You know that. You just don't bother, you probably. The first component is x1 plus x2, right, and then plus 2x3, and then plus x4. I know it's a little bit long for you guys to write, but I'm trying to multiply A and the input. The second component, you look at A in here, you look at A in here, okay? You look at X in here. I'm not copying A. So plus x4, I think. Plus x4. And then the second row, yeah, sure, thank you. The second row has components x1 and then plus 2x2 and then plus 3x3 and then plus 0x4. I do not have to include that. and then the last component. The last component is x1, and then plus 3x2, and then plus 4x3 minus x4. Okay. As long as you know how to multiply two matrices, then you know how to get this. I want to convince you a 3x4 matrix indeed determines a linear map from R4 to R3. So you see the input is in R4, right? And then the output is in R3. Okay. For the people who came in late, my intention is to use one question to show you many things about two important subspaces. One is called the null space. The null space is going to be a subspace of R4. The range is going to be a subspace of R3. Okay. Very shortly, you are going to see the definition. Actually, I will give you the definition right now. Okay. What we mean by the null space. In any case, everything is relevant to the matrix, and the matrix is the matrix determines a linear map. Okay. The linear map is from R4 to R3, so we got the linear map, right? And then we are going to talk about the null space. I think last time I gave you the definition, but I'm not super happy about the way I gave you the definition last time. So this time I'll start over. Okay, I'll start over to give you a better way to define the null space. On this slide, so probably I give you the definition only, and then so later on we get the null space. Okay. Now the definition of a null space. So how about for the definition? You could generalize, but for the definition, I just give you the definition for that matrix A. Okay. Now let's recall the null space of. Now let's recall A determines a linear map from R4 to R3, right? A determines a linear map. I'm going to use the same notation for two things. One thing is for the matrix, and the other thing is for the linear map associated with A. So there's no confusion. So because if I'm writing A colon, if I write the domain and the codomain from R4 to R3, right? From R4 to R3. Sorry, that's my 4. Probably I can make it a little better. The word thing is not gone. I was trying to write from R4 to R3. Okay. Consists of, it's a subset. So can I make it clear? I want to mention it's a subspace of what? Okay. It's a subset. Can I just say a subspace? Of course, you need to prove it's indeed a subspace. It's a subspace of the domain of R4. In order, it's either to generalize, I'm going to write the domain R4. Okay. Is a subspace of the domain R4 consisting of a better wording. Okay. Consisting of all vectors in R4 in the domain, okay, such that I will replace this with some better wording. Consisting of all vectors in R4 that get mapped to the zero vector. Okay, the zero vector in R3. The zero vector in R3. Okay. So basically, you see A determines a linear map from R4 to R3. Okay. The vectors of, the vectors in the domain under A, it can be anything in R3, right? But I'm looking for all vectors having the condition that the vectors go to the zero vector in R3. Okay. That's the official definition. In order it's easier to do questions, I will show you how to get the null space, how to compute the null space. Okay. Okay, a little comment on this. Comment. I will show you why now. Okay, I will show you why. For any input in R4, you listen to me carefully. For any input in R4, it has 4 components. The output is computed using A times the input. A times the input, right? And then we are looking for all outputs. We are looking for all inputs, all possible inputs that get mapped to the zero vector. So by that we mean you look at the mouse cursor. We want the output to be the zero vector, and then we are looking for all possible inputs. I want to repeat. This will show you how to do the calculation. I want to repeat. To get the null space, we are looking for all possible inputs having the condition that the output of the inputs is the zero vector. So basically, we want that to be the zero vector in R3. We are looking for all such vectors. So do you see we are going to solve an equation? Okay. An equation of 3 matrices actually. A matrix equation. Okay. Okay. The null space of a linear map A, or a matrix A of a linear map A. Now let's say from R, in this particular case from R4 to R3, is the solution set. Is the solution set to an equation, the matrix equation. Okay. So basically, you want the output A times. I think I was trying to use. Okay. I just include all the components. Okay. A times. So now let's say x1, x2, x3, x4. That's the output under A, right? We want the output so to be 0. We are looking for all such inputs. Okay. Anybody want to tell me how many components on the right hand side if I want to write the zero vector? How many components on the right hand side? I'm trying to write the zero vector for 3 components. So because the vectors in R4 are mapped to vectors in R3, right? In any case, we are looking for the solution to an equation like that. So it corresponds to a system of linear equations, a system of 3 equations with 4 unknowns. So very shortly, I'm going to convince that. Okay, that's the definition of the null space. Okay, it's only for the particular case when for the particular question, but the definition can be generalized. Okay, I'm trying to say you could replace 4 with m. I'm doing that right now. Okay, if you could, in general, for any matrix with m rows and n columns. You can replace 4 with m, you will replace 3 with n, okay? And then it's a subspace of the domain Rn, right? I did not use proper notations. I did not write anything wrong, but the notations I'm trying to use was not consistent with the notations I have always been used. Okay. I was trying to say you could replace 4 with n, you could replace 3 with m. A m by n matrix determines a linear map from Rn to Rm, right? And then this one is going to be n. This one is going to be n get mapped to the 0 vector in Rm, right? And then you know how to replace that, okay? So basically, so here you should have R. So how about for the comment, I just make the comment for the particular one. So it's because I have 4 components here, I have 3 components here. You just remember the null space is a subspace of the domain. In this particular case, the dot is a subspace of R3, R4. Sorry, it's because I said something wrong. The null space is a subspace of R4 in this particular case of the domain. Any questions about this? You do have questions, but your questions will be cleared after we do the questions. Okay. Now let's work on question C. In question C, we are trying to, I'm not done question B yet. I copied the wrong thing. In question B, we are trying to find the null space, actually to form the null space. My intention on question B is to show you how to compute the null space. Okay. Now the solution. After the comment, so this one is simple. Okay. Now the solution. To find the null space, we solve the matrix equation. A times, so can I write here? A times the inputs. Now let's say x1, x2, x3, x4 is equal to the 0 vector on the right hand side, right? By that we mean we are looking for all vectors in R4, such that the vectors are mapped to the 0 vector in R3. For this one, you have to solve a system, right? You have to translate the matrix equation to a system of linear equations. Okay. We have seen that many times so before the midterm. So do you see A is supposed to be the matrix of coefficients, right? And that's the column consisting of all the unknowns. So that's the column consisting of all the constants. Okay. It's a little bit long to write the system, but for this question, I'm going to do that. Okay. Now the system, you do not have to as long as you can see the system, but the system is going to be a system. So something like you write the first component. You compare the first components. So you have x1 and then plus 2x2. X1 plus x2. And then you plus 2x3. And then you plus x4. You compare the first components. The right hand side, you have 0, corresponding to that 0, right? And likewise, the second equation given by the equation of 3 matrices is x1 and then plus 2x2, and then plus 3x3. You do not have to 0 times x4. You do not have to include that term. It's equal to 0, and then the last equation is x1, and then plus 3x2, and then plus 4x3 minus x4, right, equals 0. Again, if you know what's going on, you do not have to include the system of 3 equations with 3 unknowns. You can just go from here. Now, the standard way for solving a system. Okay, standard way for solving a system. So what do we do? You copy A, right? To solve the system, we use the augmented matrix. We have seen that many times. Okay, so you have so 1 1 2 1, 1 2 3 0. Third row you have 1 3 4 -1. The last row you have all zeros. I mean the last column you have all zeros. Okay. It's easy to perform row operations to make the matrix in REF. I did that here already. All you need is to include 0 in the last column. So can I just include that thing in here? Okay. I guess I know what I'm trying to do now. It's worse. You know what? So something's overlapped. It's okay. So I'm going to rewrite everything, okay? But the final form is going to be something like the following. The final form is going to be 1 0 1 2 0, and then 0 1 1 -1 0. Trust me, I can write better on whiteboard or blackboard. And then the last row has all zeros. Okay, again, after getting the final form, so trust me, so most likely my final form is right. Even if it's not right, we can still continue. We just assume that the final form is right. Okay. Okay. Now I'm going to show you how to get the null space. By that we mean we are trying to get the solution to the system. After getting the matrix in REF, now we are ready to get the solution. Okay, we get the general solution first. Okay, the general solution. I know it's been pretty long time since we use that, but in the general solution, you identify the columns with no leading ones, right? This will give you the parameters. In this particular case, each column corresponds to a variable, to an unknown, I mean, okay? Each row corresponds to an equation. So because column 3 and column 4 are columns without leading ones, so we set x3 to be a parameter, right? We set x3 to be a parameter. So maybe we use R. So can we use R? Okay. And then you set x4 to be a parameter. So maybe use S. Okay. And then you solve the first two equations for x1 and x2. That's what we have learned before. We did many questions like those, right? And then solve the equation for x1. So you have x1. Now you watch me. You can do this better than me already. Okay. x1 in terms of R and S, I believe it's minus. It's negative R minus 2s. So correct me if you see anything wrong. Okay. And then x2 equals minus R, so negative R, and then plus S. So anybody see anything wrong? I hope I got this right. Okay. So we have the general solution. Now we are going to get the null space really soon. Okay. But in here you just need to recall R and S. R and S are parameters. By that we mean R and S can take any real numbers, right? You write something like R and S are parameters. Okay. The next thing is simple now. Okay. That's the solution. Now you listen to me carefully. We are looking for all vectors in R4 such that the output is the zero vector in here. Now we have the solution to the system. By that we mean each particular solution determines a vector in here. So that makes sense? Each solution has 4 values of x1, x2, a value of x1, a value of x2, a value of x3, a value of x4, right? So that makes sense. Each particular solution determines a vector. All such vectors will form a subspace. Very shortly, we are going to prove that. Okay, but all such vectors, I mean, the solution to the system or the solution to the equation of 3 matrices will give you all possible vectors in R4 such that the output is 0. Okay, that will give you the null space. So the null space, do I have enough space? So can I write the null space to here? This will give you the null space. I'm going to write the final answer to question B in here. So the null space, okay, the null space is the set consisting of all such vectors. The first component is negative R minus 2s is coming from x1. You look at the mouse cursor. Okay, and then the second component is negative R plus s. It's coming from x2. Negative R plus s. The third component is R, and then the fourth component is s, right? You want all such vectors. So because R and S are parameters, they can take any number. By that I mean I can make R and S run through all the real numbers. Okay, it's the old stuff connecting to the new thing. Do you know what I mean? I said the old stuff is solving a system with 3 equations and 4 unknowns. It's that. Okay, it's connected to the new thing. The new thing is a null space. Okay. Again, each particular value of R and each particular value of S will determine a vector in the null space. You let R and S run through all the real numbers. So R and S will determine many vectors in R4, right? In R4 with 4 components. Okay. All such vectors form a subset. Very shortly we are going to see it's indeed a subspace of R4. Okay. Any questions? That is the null space. You can take any particular vector if you want to try, but I'm not going to try it. Okay. You take any vector from the null space, and then you compute the output for the input you got, and then the output. You can use that. Okay, the output. I'm pretty sure they're going to be the 0 vectors. You choose any vector, the output is a 0 vector, the 0 vector. Okay. So these guys are the solution to the equation, right? That's how we get the null space. Simple. For some reason, my computer is trying to update all the time today. It's kind of slow. I don't know what's going on. I was trying to disable the update. I think it's still running for some reason. And then in question C, we're going to actually there are two ways to show that. So how about I just talk about the how to show that for the particular null space. Okay. For the particular null space, I will try to copy the null space to the next slide. I hope I can do that. We have seen that is the null space. As it's not actually, so before we can say it's indeed a null space, we have to prove it's a subspace of R4. Okay. I'm not going to go over that in details, but I will show you how. Okay. To show how you verify the three conditions, right? Verify the three conditions. So maybe we can talk about the second condition. Okay. Okay. I will give you some hint. Okay. So now let's say you choose two vectors in the null space. You choose two vectors. So now let's say can I use u and v? I think I'm going to use u and v. Okay. Probably I'm going to use the notations later, but it doesn't matter for now. Okay. You choose two vectors. So now let's say u from the null space. U in general, a null space has a form R and S can be any number, right? And then the first component is determined by the last two components. So maybe negative R, so minus 2S, and then the second component negative R and then plus S, right? And so on. You choose U in the null space. In the null space. And then so likely you'll choose another one. So now let's say V, so in the null space. And then you want to show U plus V is still in the null space. I put a question mark to mean you do this on your own. Okay. It's in the null space. So we have seen a question like that too many times. I believe all of you guys can do that. Okay. And secondly, after that, you can say the null space is closed under the vector addition, right? And then secondly, you show the null space. The null space is closed under scalar multiplication. Do this on your own, please. Okay. And then lastly, it's not very necessary. Show the zero vector is in there. Okay. Can I skip that step? In question C, I think we have seen too many questions like that. Okay. It's the same thing as the questions we did before. Rather than C. Okay. Now we move on to question D. It's also the old stuff. I think we have seen the idea many times already. In question D, I'm trying to get a basis of the null space. A basis of the null space. So this time I will copy the null space to the next slide again. Okay, now we are going to get a basis of the null space. Again, you look at the components of the vectors in null space. R and S can take any number. After taking the values of R and S, and then the first two components are determined by the third component and the fourth component. Anybody want to suggest at least one how to get the values of, how to get a basis? We claim, so we have seen that over and over again, right? We claim what? So what will form a basis of the null space? The same as before, R and S can be any number, right? Can take any number. By that we mean R value of 1, S value of 0 will give you one of the two vectors. I think I can tell two vectors. Okay, 1, 0. If R value is 1, S value is 0, then the first component, I believe, is -1. The second component is -1 as well, right? You choose two vectors from the null space. We want to show the two vectors, they form a basis. And so that's one of the two vectors I want to choose. The second vector, we have seen that before, right? R value of 0 and S value of 1 will give you another basis vector. Okay. If R value is 0, S value is 1, I believe the first component is -2, the second component is 1, right? So correct me if you see anything wrong, okay? Thank you. We claim these two vectors, so maybe a better wording is and, not vector and that vector. The two vectors form a basis of the null space. I think you can see we just repeating many things we learned before for the null space, a particular important subspace of R4 of the domain, actually. Okay. From a basis of the null space. How can we prove that? Okay. Indeed, or in fact, now you recall the two conditions. To say a subset of, now let's say R4, to say these two vectors form a basis of the subspace. To see these two vectors from the null space form a basis of the null space, we want to show two things. One thing is every vector in the null space is a linear combination of the two chosen vectors. Okay. By that we mean we want to show they span the null space. Okay. So anybody has connection problem? No? I see some people come and go. Okay, we have seen the idea, right? So by that we mean we want to show each vector in the null space is a linear combination of the two vectors. Okay, each vector. So now let's say -r minus 2s, and then -r plus s, and then rs. That's every vector in the null space has that form in the null space. So probably I should have introduced a notation for the null space. And by the way, people also call null space kernel. Kernel. I said kernel. I think an EL, kernel. The same thing as the null space. Okay. We want to show each vector in the null space is a linear combination of the two vectors. I think we have seen that many times. So this time I'm not going to ask you. Minus r minus 2s minus r plus s, right? Any vector in the null space can be written as a linear combination of the two vectors we want them to be a basis. Okay. The coefficients I believe you can see are r and s, right? R times -1, -1, 1, 0, and then plus s times -2, 0, 0, sorry, 1 in here, okay, 0, 1, a little messy, but that's okay. Okay, I'm recording the lecture anyway. Okay, if you have connection problem, you can watch the you can watch the videos later. Okay. Okay, so We have seen that many times. You know it's true. Okay, you know it's true. So by that we mean the two vectors. So maybe I will write the conclusion. Okay, the two vectors span the null space. That's one of the two conditions. The second condition you have to do is to verify the two vectors they form a basis of the null space. I mean the two vectors they are linearly independent. Okay, to show that we can use the shortcut method. Okay, you put the components in columns -1, -1, 1, 0, -2, 1, 0, 1, and then you perform elementary row operations. So you see I'm not asking you too many questions. So so this is the first time I'm using a new way to motivate the null space and the range. I don't know how much time I'm going to use. Performing row operations, I believe the final form you're going to get is 1, 0, 0, 1, 0, 0, 0, 0. You could check that. Okay, I'm pretty sure that's right. Now, using that, I'm trying to show you the given two vectors are indeed linearly independent. Now, let's recall the shortcut method. Okay, to answer that, you check the columns. In this particular case, every column has a leading 1. Every column has a leading 1. I'm trying to say no columns without leading 1s, right? That's the condition under which the given vectors are linearly independent. Okay. So the given vectors, these two vectors. So because I have too many notations, I do not want to introduce too many notations. Okay. So these two vectors, -1, -1, 1, 0, and the second vector, -2, 1, 0, 1. The two vectors they form a basis. So do not stop here. You need to say from a basis of what? From a basis of the null space, right? Again, the given a linear map or a matrix, so there are two important subspaces. One is the null space, the other one is the range. Okay. You can see for the final, I do not have to include system of equations. So because it's covered in a question like that already, right? I will talk about the final sometime later. Okay, but it's been scheduled. I told you before. Okay. So we're done. We're done. Question D. After you can get a basis, after you know the dimension, and then you kind of understand the subspace already. Okay. I believe in question E, we're trying to get. You look at the question. We're trying to get the dimension of the null space. Okay, because I'm here already. I'm going to I will copy the question anyway. Okay. The dimension of the null space. So we have now. Let's recall the definition of a dimension. Dimension is by definition it means the number of basis vectors in any basis, right? I'm trying to say the null space. If you sketch in the four-dimensional space in here, it's a two-dimensional thing. Okay. I know R4 is a little bit abstract, but you just try not to imagine that. You just try to treat R4 as a set consisting of all vectors with four components. Okay. So the dimension of the null space is 2. So because there are two vectors a basis we just found. Okay, so that's null space. I think these are all the questions about the null space. On Friday's quiz, so probably I could reduce the size of the matrix. So, but for the lecture, I'm going to use something more general to show you all possible cases. No, we're not quite done the null space yet. We found the dimension already. One more question for the null space. In this particular case, we are trying to determine if the given linear map is 1 to 1. 1 to 1. I don't know if you learned the term in high school or not, but I'm going to tell you the meaning. A map is 1 to 1 if it maps so different. I have a typo here. Sorry. We're trying to determine if the map A is from R4 to R3, of course, right? It's from R4 to R3. I'm going to correct that later. We're trying to determine if the map is 1 to 1. Actually, the definition is true in general for any map. To say a map is 1 to 1, I will write the definition. So definition, to say a map, so now let's say from A to B, I'm going to write the general definition. It's 1 to 1 if the different members of A of set A are mapped to different members of set B. I will show you one particular case that is not 1 to 1. So now let's say if F is a map from real numbers to real numbers, if every number is mapped to the number squared. Now try to follow me, If I'm looking for the output for the input of 1, so you see 1 goes to 1, so this one is 1 squared. If I'm looking for the output for the input of -1, -1 goes to under that F goes to, it also goes to 1, right? This one is not 1 to 1. It's not 1 to 1, right? So because you have two different inputs giving you the same output. You look at the definition again. You have to say a map is 1 to 1 if different inputs will give you the different outputs. So that's not the case. So this map is not 1 to 1. That's the definition in general. But for linear maps, we can use the null space to determine if a linear map is 1 to 1. I will write you a conclusion. So can I just say it's a fact? A linear map is 1 to 1. You can use the kernel. I mean the null space. I did not say anything wrong. Kernel is for the null space. The same term. A linear map is 1 to 1. Actually, if and only if the null space of A. Can use this notation to denote the null space of A. If and only if the null space of A I mean, the dimension of the null space of A is equal to 0. I think we haven't seen too many subspaces with the dimension of 0. But we mentioned before, a subset consisting of only one 0 vector is a subspace. That's the only subspace having the dimension of 0. I mean, if the system in here has only the 0 solution, then the null space is the set consisting of only 0, right? In that case, the null space is equal to, I mean, the dimension of the null space is 0, only in that case. Okay. If you have any non-zero vectors, then the dimension of the null space is not equal to 0. Okay. We're not quite done yet. So we haven't answered question F yet. Okay. I will copy F to the next slide. We're going to answer question F. Okay. Is the answer yes or no? The answer is no, right? So because the dimension of the null space we found was 2. Okay. So maybe the answer now, since the dimension of the null space we found was 2, okay, which is not 0, then it's not 1 to 1. Okay. The linear map A from R4 to R3 is not 1 to 1. Okay. So good enough. To convince you, you have to find two different vectors that are mapped to the same vector. To find two different vectors is simple now. You just choose any two vectors in the null space. I'm trying to say you just choose any two non-zero vectors from the null space. Okay. So how about we just use the two basis vectors? I'm kind of running faster than normal. I hope you can follow though. It doesn't matter. Okay. For these two, for these two vectors, so in the null space, again, to answer the question, you just choose two different vectors from the null space, such that the output. Now we're going to compute the output. Okay. We have, these are two different vectors, right? We have the output for the input of -1, -1, 1, 0. So because these two vectors are from the null space, the output has to be the 0 vector, right? The 0 vector. And also the output for the input of -2, 1, 0, 1 is also the 0 vector. So do you see why? You do not have to compute. So because the two vectors are from the null space. Okay. These two vectors are satisfying the conditions that these two vectors are different, of course, right? But the output of two different vectors are the same, right? For the questions we're trying to answer as required. Okay. We wanted to, now you look at the question. We wanted to find out two different vectors in R4 that are mapped to the same vector in R3. Now you are convinced A is not one-to-one? Okay. Okay. Probably we're done the null space. We're done the null space. Okay. Now the following questions are designed for the range. So maybe long time ago I told you the meaning of the range. I'm going to define that again. Okay. So maybe the range, now the definition. The range of the linear map from R4 to from R4 to R3 is the set consisting of all possible outputs of vectors under A. Actually, I do not have to write the thing. The meaning is clear now. Okay. So basically, each vector in R4 under A, you can get the output, right? And then you get all possible outputs. They form the range. All the following questions are designed for the range. Okay. Now we'll work on question G first. Okay. So because the notations in R4 are going to be a little weird. In R4, so there should be 4 standard spaces vectors. So that makes sense. I1, I2, I3, and I4. I do not want to use ijk anymore. Okay. So maybe now let's try to do that. Okay. So maybe I1. We have 4 equations to verify, so we just do one of them. Okay. So maybe I1. You want to guess the meaning of I1? I1 in R4, so there should be 4 standard spaces vectors. So comparable to ij and k, is a vector with only the first component 1. 3 other components are zeros. Okay. So that's I. Likewise, I believe you can imagine the meaning of J. Okay. I mean I2 has only the second component 1. 3 other components are zeros. So that's I2. Okay. And by the way, the notations may not be standard, but I'm trying to use I1 up to I4 to denote the 4 standard spaces vectors in R4. Okay. What I want you to compute is the following. Now we are trying to compute the output for the input of I. Okay. The output for the input of I is given by A times I, right? The output for any input x1, x2, x3, x4 is given by A times x1, x2 up to x4. We have seen that. Okay. Now we just want to compute the output for the input of I. Multiply 2 matrices. I think it's simple to verify. You just use A to, you look at the mouse cursor, you use A to multiply I. Anybody can tell me very quickly? So what's AI? Very quickly, please. Very quickly. I think you're working on that. I can tell you the answer now. Okay. Yeah, 111 is right. Okay. You just multiply A and I and I1. I mean A and I1. Now I want you to see that's actually the first column in matrix A. So that makes sense? That's the first column in matrix A. I think you have seen the pattern already. Now you can tell me the answer to to A times I2. A times I2 is going to be the second column of A. Okay, is the the vector with components 1, 2, 3. That's the second column of A. Okay, and likewise I really do not have to write them all. I think you have seen the pattern already. You have 2, 3, and 4. And the A times I4, I'm going to write them all. Okay, you have 1, 0, and 91, right? That's my question G. My intention is that I want to show you the output. Now let's recall it's relevant to the range. The range is the set consisting of all outputs. Now in question G, we are trying to get all the outputs for the standard spaces vectors as inputs. Okay. Now you remember the outputs for the I1, I2 up to I4 are just columns in matrix A. So that makes sense? Okay. So that's the answer to question G. After we do question H, and then I will show you how to form. I will show you a conclusion, how to get the range. The following question is designed to show you why. Okay, to show you why the range is given by something I'm going to tell you soon. Okay. In question H, we want to show that for each vector in R4, the output for each vector in R4 is a linear combination of the column vectors. So can I just say V1, V2, and V3 and V4 are column vectors of the matrix A? You see V1 has all the components in the first column, right? V2 has all the components in the second column, and so on. Okay. We want to show that. Okay. To show that, for each vector u in R4, for each vector u in R4, u has 4 components. U has 4 components. So can I just try to write the 4 components? Okay. So can I write? I'm going to use A, B, C, D to denote 4 components. You could use X, Y, Z, T. You could probably the better notation is to use X1, X2, and so on. But it doesn't matter. Any vector in R4 has 4 components. Okay, for each vector u in R4, you imagine that's a vector in the domain. So do not lose track. A determines a linear map from R4 to R3. Everything is relevant to that A. Okay. Now we choose each vector u in that R4. Okay. So because we have seen the outputs for standard basis vectors, right? Now I want to connect that to the standard basis vectors. We have u can be written as a linear combination of the standard basis vectors as what? I think we have seen that before, right? So that makes sense. It's A times I1 and then plus B times I2 and then plus C times I3 and then plus D times I4, right? That's how we write U in terms of standard basis vectors. Now we are trying to show the output for the input of U. Now you look at here. This notation is it's the output for the input of U, right? U is a vector in R4. Every output you just multiply on the left by A. So that makes sense? Okay. So we have A times U. A times U is equal to A times, you just copy the representation in terms of standard basis vectors. A times AI1 and then plus BI2. So that means a 2 in here. And then plus C times I3 and then plus DI4 A is linear. We have seen A is linear. So by that, A preserves vector addition and scalar multiplication. I will give you the next step. You will know what I mean. Okay. The next step is A times AI, right? And then plus B times, AI1, and then B AI2, and then plus C AI3. Again, A preserves vector addition and scalar multiplication. By that we mean A preserves linear combinations of any vectors in R4. Okay. I4. Okay, so what's the final answer? I want to remind you AI1 is actually the first column, right? It's AB. AB1, AB1. V1 has all the components in the first column, and then plus BV2. V2 has all the components in the second column, and then CV3. CV3 has all the components in the third column, and then DV4. Right. You can follow me, right? Now I want you to see the following. You listen to me carefully. I want you to see the following. The output of any vector u in R4, the output of any vector u in R4 is a linear combination of the column vectors in matrix A. That's something I'm trying to tell you. I want to repeat. The output of any vector in R4 is a linear combination of the column vectors in matrix A. What should be all possible outputs? What should be all possible outputs? Every output is a linear combination of the column vectors. So does that make sense? The output, the range. The range is a set consisting of all possible outputs, right? All outputs should be all linear combinations of V1, V2, V3, and V4. All outputs should be all linear combinations of the column vectors in matrix A. Okay. So that's something I want to motivate. Okay. I think you have seen why. I'm going to write down the conclusion. Okay. The conclusion. The range of A, the range of the linear map A from R4 to R3. So in this case, you could generalize that. Okay, can anybody recall the meaning of the set consisting of all linear combinations of V1, V2, V3, and V4? I have another table. It should be V3. I think you have seen the table a long time ago. Okay. It's actually the spanning set. You want to recall the meaning of the spanning set? The spanning set is the set consisting of all linear combinations of V1, V2, V3, and V4. Okay. Probably 2 weeks ago, we did many questions about the spanning set of some vectors. Now you see the connection again, right? Now the following questions are going to be old questions. Okay. You know, the way I'm doing the material today is kind of so different from my normal thing. I normally run pretty slowly, but so today I'm kind of running at my old regular speed. I think we can probably do all the questions all the questions together. So because the problem has been converted to the old problem already, right? Now, for question 1, in question 1, according to the fact I just told you, the range is a set consisting of is the set consisting is the set spanned by v1, v2, v3, and v4. Okay. So the answer to question 1, the range is the spanning set of v1, v2, v3, and v4. You see all the questions. You know how to do all of these already, okay? If you want to write the meaning as a set consisting of all the linear combinations, right? I don't know what notations you want to use. So can we just use x1, x2? Actually, the notations are kind of consistent with notations we used earlier, okay? Or we could use ABCD, right? Now let's use ABCD, AB1, and then plus BB2, and then plus CB3. You know the spanning set is the set consisting of all possible linear combinations of the given vectors. And you let ABCD run through all the real numbers. You can treat that as the answer to question I. Okay, the spanning set. That's actually the meaning of the spanning set. Okay. In question J, you look at question J. Okay. In question J, we are looking for a basis of the range. We have seen the range is the spanning set. On the top of the screen, I gave you the final form. I mean the REF for A. Okay. Using the thing we did 2 weeks ago. I may not have time to go over the thing in more detail, but using the knowledge we learned 2 weeks ago. Okay. Now you look at the final form. Okay. You look at the final form. I will write something in some more details. Okay. You look at the final form. In the final form, you listen to me carefully. Okay. The third column is a linear combination of the first 2 columns, as the third column is 1 times the first column and then plus 1 times the second column. We mentioned a long time ago. If that is true, then it's true for the given v1, v2, v3, and v4. I'm trying to say, using the final form, so maybe for question J only, the solution key. When I'm writing key, it's not the detailed solution. Okay. I'm trying to say v3 now is a linear combination of v1 and v2. You can also check that, okay, as v1 and then plus v2. Actually, I did not use too complicated numbers. You can check that. So directly from here, okay. 2, 3, 4 is the first column and then plus the second column. In general, you can see the coefficients from the final form. You'll see column 3 here is 1 times column 1 and then plus 1 times column 2, right? The same idea. I'm trying to say v3 is a linear combination of v1 and v2. It's kind of saying v3 is redundant, right? In terms of determining forming the linear combination. Okay, v3 is that, and likewise you can represent v4 as a linear combination of v1 and v2 as. So very quickly, so anybody? I'm looking for the 2 numbers, 2 coefficients, please. 2, -1, right? I'm trying to say v4 is 2 v1 and then minus v2. it's kind of mean V3 and V4 are redundant, are not necessary. Can I say that way? In terms of forming the spanning set. Okay. After you see that, you want to show. Anybody want to guess a basis of the range? The basis of the range, please. So just
V1 and V2.
V1 and V2. Okay. I'm not going to show in details. So, but I think we did many questions like that already. Okay. So V1 and V2 only form a basis of the range. So question mark. I'm using question mark to mean you need to show some work. You need to show some more work. Okay. You need to show V1 and V2 are linearly independent, right? You also need to show every vector in the spanning set is a linear combination of V1 and V2 only. Okay. After that, we can answer question. Yeah, K. For question K should be simple, right? If I have time, I will go back to that question to show you the details. But I want to move on to question K now. Okay. In question K, we are looking for the dimension of the range. Okay. The dimension of the range. So because so there are two vectors in a basis, so the dimension of the range is equal to 2. So that makes sense. The dimension is the number of basis vectors in any basis. Okay. So we're done question K. Now let's work on question L. Okay. In question L, so there's a connection between a term onto and I will start a new slide. Okay. So definition, I'm trying to define what we mean by onto. Okay. A map. So now let's say F from a set A to set B is onto. Maybe it's said to be onto. It's said to be onto. If what? If the range, I told you the range already, okay? If the range of the function of the map is the same thing as B, if the range is the same thing as a Codal map, okay? So by that we mean if you get all possible outputs, it will fill up the Codal map. In that case, we say it's onto, okay? And another conclusion, okay, a linear map, so maybe a fact, a linear map is onto a linear map. So maybe can I use the particular case? A from R4 to R3 is onto if and only if the dimension of the range is equal to 3. You know the range is a subset of R3 in this particular case, right? To show it's onto, all we need is to show the dimension of the range is the same as the dimension of R3, so which is 3. Okay. After that, we can answer the last question. I think. I did not want that. Now the last question, okay? So question L. Is A onto? A is not onto, right? It's because the dimension of the range we have seen is 2, right? Since the dimension of the range is equal to 2, so which is not the same as 3. So it's not onto, okay? One more question, okay? I mean, you're not done the last question yet. If it's not onto, the most way to convince people is to find a vector in R3 so that it's not in the range. I want to repeat, the most convincing way is to find a vector in R3. I mean, a vector in R3, right? That is not in the range, so it's not onto. No vector will get mapped so to that vector. Okay. Yeah, probably I do not have time to go over the thing in details. But I will give you a hint. Okay. So maybe a solution key to the next part. On the quiz, I'm not going to include this part, but I'm trying to say the most convincing way to tell people it's not onto is to find a vector in the codomain, so that is not in the range. Okay. The vector in the codomain, try one of the 3 vectors. I think in this particular case, we want to show. You say something like we claim the vector I 1 0 0. That's the vector I in R3. Okay. Most likely that will work. So because we did not change any row when performing the operation. Okay. We claim that vector I is not in the range. To show that, so maybe to show this, to show this, I'm trying to find a better wording. So can I write show twice to prove this? I'm going to turn that to prove this. To prove this, show that the output for any input, for any input. So now let's say x1, x2, x3, x4. That's the output for any input x1, x2, x3, x4. Okay. To show that, you need to tell me. So this thing has no solution. That equation has no solution. Which means no vectors in R4 are get mapped to that I. Okay, 1 0 0. Again, that's the most convincing way to show it's not onto. Okay,